Hello everybody, it's Mrs. Avon again. For our last video in Chapter 9, we're going to look at two-dimensional collisions. All of the collisions that we've been studying so far have been one-dimensional. They've been head-on or rear-end collisions. Clearly, all collisions that occur aren't in one dimension. So we're going to look at two specific cases of two-dimensional collisions where things either come into the collision or leave the collision at angles to each other. The two specific ones that we are going to look at is when two objects come together and stick together, which we call an inelastic collision, or when they leave a collision at 90 degrees. Clearly, if you've ever watched anyone play pool, you know that all interactions are not head-on, rear-end, or at 90 degrees, but those are the only ones that we are going to study in this class, because when they're at 90 degrees, we can use the trig functions, sine, cosine, and tangent, and we can use the Pythagorean theorem to solve the problem. So we're going to look at two examples, one example of an elastic and one example of an inelastic. Momentum is still conserved in two-dimensional collisions, so our equations are going to look very similar. Our first example, and these both come from the textbook, is we have a stationary billiard ball, so we're talking about pool. It's struck by an identical ball, which means it has the same mass, and after the collision, one goes 60 degrees to the left and the other one goes 30 degrees to the right. So it's very important that while you will have the initial equation, that you draw the picture. What is happening? So I start out with two billiard balls. We just set M2 at rest and just do that every time so it's consistent. So I start out with M1 V1 moving into M2 V2, which is stationary, it's at rest. M1 leaves the collision at 60, M2 leaves the collision at 30. So the 60 degrees is above the horizontal, the 30 degrees is below the horizontal. I know by now that I cannot add vectors unless they are tip to tail. So I redraw the vectors V1, V2 so that they're added tip to tail. And then the hypotenuse is the total momentum before, M1, V1. Once I have a right triangle drawn, all I need to do is use either the Pythagorean theorem or sine, cosine, and tangent in order to solve the problem. So if I want to find one of the sides, either V1 prime or V2 prime, remember prime just means after, all I have to do is plug it into cosine 60 equals adjacent over hypotenuse. Instead of writing adjacent and hypotenuse, I plug in what sides of the triangle, M1 V1 prime over M1 V1. Technically, in this case, the masses cancel out because they are identical, but I left them in there in case you see an example where they're not the same. When you plug that into your calculator, and the point of putting that blocker up there is for you to try these and then play the video so that you can look at the answer. So when I plug in for V1 prime, I get 2 meters per second, and I know it's at 60 degrees to the left. I didn't have to do any math for that. The picture shows me. Then for sine, it's opposite over hypotenuse. So M2 V2 prime over M1 V1. I rearrange it for my unknown. I plug it in and get 3.5 meters per second. And I know that's at 30 degrees to the right. The problem tells me the direction. I don't need to figure that out. So I'm going to use either the Pythagorean theorem or sine, cosine, or tangent. Once you figure out one of these values, once I figured out 2.0, I could actually use the Pythagorean theorem to figure out V2 prime because I would know the other sides of the triangle. So there's always more than one way to solve these. The second example would be for an inelastic, same conservation equation. The total momentum before equals the total momentum after, but they're stuck together, so I have a combined mass and a velocity. In these problems, it is very important to watch the direction of the original vectors. It could tell you some are going east and north, or south and west, or south and east, or west and north. So make sure that you read the problem and draw the vectors accordingly, tip to tail. So I have two cars, one's moving north, one's moving west, and after the collision they stick together, and it wants to know the speed and direction of their momentum after the collision. So the first thing I do is draw the picture. I draw M2V2 to the left, which is west, and I draw M1V1 to the north, and then my resultant is in orange. That represents the total momentum after. To find the angle, keep in mind I'm in the second quadrant, I just take the tangent of the adjacent over the opposite over the adjacent for tangent, M1V1 over M2V2, and I get 36.6 degrees. In order to find the magnitude, I can then use the Pythagorean theorem. That's all you see at the top of this page is the Pythagorean theorem. A squared plus b squared equals c squared. So I rearrange my equation. First I distributed the squares on the m1 plus 2 v prime so that I could separate them, rearrange it, get my final equation, plug it in. Anytime you see parentheses on this screen here, you should be using parentheses in your calculator with a times sign in between them. I would do the numerator first, get an answer, then divide by the denominator. When I plug all that in, I get a final velocity. They're combined, so it's just 1 v prime of 11.2 meters per second at 36.6 degrees. But because I'm in the second quadrant, I have to say north of west or 143 degrees. So we're taking what we learned about the conservation of momentum and what we've previously learned about triangles, and we're putting those together for the last problem type in this chapter.